Hello, welcome to today's video where we're going to be looking at multiple matrix transformations, both how to apply multiple matrix transformations if you're wanting to do the transformations yourself, or also how to identify what transformations have happened if somebody else has already transformed something with multiple transformations. So let's start off by looking at how to apply multiple transformations. And at first you might be thinking, why am I showing you this? Because ultimately, if you want to apply multiple transformations, you can apply them individually, one after another, by using the same process that we looked at before for applying matrix transformations. For instance, if we wanted to apply a transformation A to a point X first, then we could apply it using the logic we've talked about before for matrix transformations, which is to do the matrix representing transformation A, let's call that matrix A, times by the matrix representing the point, and that will get us the transformed version of that point. If we then want to apply a second transformation, we can then do that individually as well. So if we're applying transformation B to our transformed point, we'd do B times by our transformed point to get the point that's been transformed by both of those transformations, and I'm going to refer to it with the notation X apostrophe apostrophe. So there you go, and therefore yes, we can apply multiple transformations individually to get the result of those multiple transformations. However, interestingly, if you're applying multiple transformations, there is an overall effect that we can observe. Instead of having those transformations as separate matrices, we can express the multiple transformations as one single overall transformation matrix. How does that work? Let's take a look, because if you look at these two equations we've written, you could view them as simultaneous equations, because both of them involve X apostrophe, i.e. the point that had been transformed once. And therefore we could use that as a substitution to eliminate that in these two equations. So for instance, if I substitute the first equation into the second equation, we'll end up with B lots of AX equals X transformed twice. So what does that tell us? Well, it tells us that if we want to transform the original point all the way to get the point that's been transformed by both transformations, we've just got to multiply by the matrix BA, which is interesting because that kind of looks backwards to what we're expecting. We applied transformation A first, then transformation B, yet the overall matrix we're having to multiply by is BA, in other words, the opposite order. So yes, that is noteworthy, and therefore it's something you're going to need to remember off by heart. If you want to do matrix A followed by matrix B, you have to multiply by BA. And so let's take a look at an example. So there's of course a lot of words on the screen right now, so you're welcome to pause the video to give yourself time to have a read through that first. But an overview of the question is basically we've got a transformation P, which is a rotation. We'll look at that in more detail when we get to solving the question. We've got a transformation Q, which is a stretch. Again, we'll look at that in more detail in a bit. But the important point overarching throughout this question is the fact that we're doing transformation Q first, and then following that we're doing transformation P second. So we've got multiple matrix transformations being applied here. We want to find the matrix representing this permutation of transformations in part A, which is basically saying what's the overall matrix that represents the combined effect of these transformations, and then in part B applying that overall one big transformation to specifically the point X. So therefore, let's get going. Of course, if transformation P is a rotation, that means we can start using the formula booklet, because that's of course where the rotation is written. It's a rotation anti-clockwise about O, which is good because that means that's tallying with the structure of a rotation that's given in the formula booklet. The rotation is 90 degrees, that means our theta is 90 degrees. So that means we can start to write down what the matrix would be, because it would be cos of 90 degrees minus sine of 90 degrees, sine of 90 degrees, and of course cos of 90 degrees. And therefore, those are ultimately all numbers we can find. So P is just the matrix 0, minus 1, 1, 0. Lovely. Transformation Q is a stretch, scale factor 7, and it's parallel to the x-axis, importantly. That's important because that means it's just going to be a matrix that looks very similar to the identity matrix, but the 1 in the top left-hand corner is replaced by a 7 because of that scale factor 7. And it's the top left-hand one that's being replaced because it's parallel to the x-axis. A reminder, if it is parallel to the y-axis, it would be the one in the bottom right that we'd be replacing instead. Cool, so we've got P and Q individually now, but we're doing transformation Q followed by transformation P, which you might remember from the slide before means although it's Q then P, we've got to do the matrix PQ as a result. So therefore part A is simply going to be PQ, which would equal 0, minus 1, 1, 0 times by 7, 0, 0, 1. And then you just got to work that out by doing matrix multiplication. If you were to do that, we'd end up with a 0 there, we'd end up with a minus 1 there, we'd end up with a 7 there, and we'd end up with a 0 there. And there you go, that's the answer to the first part of the first question. And then part B, applying these transformations to the coordinates x, you've got some options. You could then go back and individually apply first transformation Q to the point, then apply transformation P to that point, but that would take much longer than just applying straight away this matrix we found in part A to our coordinates. So therefore that's the quick way of doing it now. Just do this, the answer to part A, times by the coordinates, rewritten as a 2 by 1 matrix, and then we will get our answer when we multiply those together. So therefore, if we multiply them together, we'll end up with minus 5, and then we will end up with minus 14. There you go. So that is the answer to the question. Again, do watch out for the wording. Did the question ask the answer to be coordinates? It didn't, so I would get away with it. But if it did ask for coordinates in the final answer, you would have to, if you want to guarantee the marks, rewrite the final answer as coordinates like that. So that's how you apply multiple transformations. But what happens if you want to identify what transformations happened if multiple transformations are involved? Well, good news, because they should tell you what type of transformations are involved, and there's a very good reason for that, because ultimately if you're just told, okay, 2 transformations have happened and it results in this overall matrix, the unfortunate aspect of that is there's technically going to be infinite answers to that question. For instance, even if we're just having a very at first simple idea like saying there's 2 matrices and they result in an overall effect of a rotation of 60 degrees, there's infinite answers to what those 2 matrices could be, even if you just put in the restriction of both of those 2 matrices have to be rotations, because if you're doing 2 rotations that result in a rotation of 60 degrees overall, that means we could have a rotation of 10 degrees followed by a rotation of 50 degrees, or a rotation of 20 degrees followed by a rotation of 40 degrees, etc, etc. There's infinite ways I could express 2 transformations resulting in that one overall transformation. So therefore they should narrow it down for the sake of the mark scheme, if anything, what 2 transformations have happened to cause the overall effect, with just maybe some details missing, like parameters. Like if you're talking about a stretch, what's the scale factor? That might be the part that's missing. Or if it's a rotation or a reflection, they're not telling the reflection line or the amount it's rotated by, that sort of thing. And then the other thing they should probably tell you is what order the 2 matrices that are involved happened in, because ultimately, again, there would be a bit of guesswork involved otherwise, which, you know, there's nothing stopping them in theory asking that, but they would be very mean, and I can't foresee them actually going ahead and doing that based on previous experience of exam questions I've seen before. But it is worth mentioning there's one exception to that, and that is if an enlargement transformation is involved, because ironically, if an enlargement transformation is involved, it actually doesn't matter what order the transformations are applied in, because an enlargement is just a multiple of the identity matrix, and the identity matrix as we discussed when we talked about the identity matrix originally, is a matrix that order doesn't matter when it comes to multiplication, which is unusual for matrix multiplication, of course. So, with all that said, if they've given you that information, how do you then go about it? Well, all you've got to do is to use the generic formulas for the transformations that are involved, multiply them together in the order that's been shown, and then use that to set up some equations comparing the elements in your matrix or the matrix they've been given to you, and use that to create some simultaneous equations to solve. So, the best way to show that is to just do an example, because describing it sounds horrible. So let's do an example. So we've got transformation A, which is an enlargement. We don't know the scale factor. That tallies with what I'd said on the previous slide. Transformation B is a reflection. And again, we don't know the line of reflection. So again, they tell us what the transformation is, but they miss out some details to do with it. The combination of these transformations, that's very vague, that's not telling us the order, but we are expecting that because this question's involving an enlargement, and therefore, as I said before, order doesn't matter if an enlargement's involved. So, with that said, we can start by just taking the formulas for these two matrices and multiply them together. As I said, because enlargement's involved, it doesn't matter what order, so I'm going to do the enlargement first for no reason other than it was written first. So it's just the first one that comes to mind. The formula for reflection, of course, you can use the form booklet to know what that is, because it's written in there, just like it is for a rotation transformation. Okay, so those are our two transformations. We can then go ahead and multiply these two transformation matrices together. And because they're nice ones, that's actually going to be very easy to do. Because the enlargement matrix is just going to result in everything being multiplied by k, which is good because it makes it very quick to do. Nice. Now, that is the matrix we got if you combine a enlargement with a reflection. But the question says we had an enlargement and a reflection combined, and it came together to make the matrix that they have shown written in the question. And our matrix and the matrix they've got should be the same matrix, but obviously currently they're not. So therefore that instantly tells us some mini equations that we can set up. These equations have to be true in order for these two matrices to end up being the same eventually. So therefore k cos 2 theta, by comparing the top left element in both matrices, has got to equal 0, and comparing the top right element in both matrices, we can get that k sine 2 theta equals -3. Now, normally when trying to set up equations based on the elements in matrices, you should do that for all of the elements in the matrix, but it's just that if we do the bottom left elements and the bottom right elements, you're just going to get repeats of the two equations we've had already. But it is worth having a quick visual check to make sure there isn't additional information that will be obtained by having an equation set up from those things as well. Now, for these very specific equations we've got right here, they do look very similar to, depending on how much maths A-level content you've covered at this point in your education, but this looks very similar to the style of equations we solve when doing harmonic form in trigonometry. However, although there are some similarities to it, you do have to be careful. So there are some slight deviances from this, so do pay attention even if you have come across that stuff before. Ultimately, the quick way of getting k would be to just do Pythagoras with the two numbers on the ends of the equations. So the square root of 0 squared plus -3 all squared. And of course, if you were to do that, you would get 3. To know why that's going ahead, it's all about just trying to rearrange these equations to make the trig functions the subject to the formula, and then plug into the identity sine squared 2 theta plus cos squared 2 theta equals 1, which is a trigonometric identity we always know is true. Okay, so we've got our value of k, it's equal to 3, so therefore part A is already done. Nice, I should have probably labelled part A somewhere, so let's put it there. So therefore on to part B, and ultimately it is just continuing on what we had already started. We need to fully solve these simultaneous equations to find theta, because theta will help us define what type of reflection we're looking at. So therefore, instead of solving these simultaneous equations in the same way that we did for harmonic form, you're going to want to solve these equations in the same way that we do normally for matrix transformations, for rotations and reflections, which is to basically solve the equations individually and then just try and find the value of theta that works for both equations. Find which one overlaps. So therefore, solving the first equation, of course, divide both sides by 3 first. You can find the first solution to 2 theta by using arccos of 0, which is 90. You can, of course, get a second solution by doing 360 minus 90, which would be 270 degrees. I will bother dividing by 2 to get theta in a bit, because ultimately I could just move on to the second equation and try and find values of 2 theta there as well, and basically whichever value of 2 theta overlaps will also cause the value of theta that overlaps. So I've already divided both sides by 3, and now to get a value for 2 theta I could do arc sine of minus 1, which would be minus 90, which is a bit annoying, but ultimately you could get a second solution by either doing 180 minus 90, which would get you, interestingly, 270 degrees. Another solution then could also be potentially attained by doing minus 90 plus 360 degrees. Interestingly, that would also get you 270 degrees. So therefore, actually, there is only one solution that matters for the second equation, and therefore we can already see the one that overlaps is 270 degrees, but watch out, that's the value of 2 theta. So we need to find what the value of theta is, and that would be 270 divided by 2, which would be 135 degrees. There you go. Tan of 135 degrees is equal to minus 1. So therefore, part B, the answer to part B, is it's a reflection in the line y equals minus x. Y equals minus x because the form booklet says it's a reflection in the line y equals tan theta of x. We now know what theta is, so I just plug it into that structure and get y equals minus x, because tan of 135 is minus 1. So there you go. That is the answer to this question. Now that was me showing a general approach to dealing with these questions where you have to identify what transformations have gone on, but ultimately there is sometimes an alternative approach you can take involving determinant, and that's also true for this question, because ultimately you can make use of the fact that determinant has a strong link to enlargements, which is that enlargements have a determinant of k squared, so therefore instantly from the determinant of the overall matrix you have something linking to k squared, whereas the determinant of rotations and reflections are 1 because they're things that don't enlarge the area of something. So therefore you could set up that k squared is equal to the determinant of the matrix given the question, therefore k squared equals 9, therefore that's an alternative way of doing part A. Part B would still be done in the same way, and ultimately, therefore, that's it for today. I'll see you in a future video. Hopefully you found this video useful, and goodbye.